Hello, everybody. Welcome back. My name is Michael. I hope you're having a wonderful day so far. Today is December 11th, 2024, and we are back streaming trying to learn some Python. Hope everyone is having a great day, is feeling good. Um, just another day back at work, right, for me. Let me get my AirPods case here. Got started on a project here at work that I've been prepping for a few weeks now, and so it's finally getting started here, which is good and should be fun. But yeah, let's get some. Let's go ahead and let the Discord know we are live. Cool. All right, let's go ahead and get started here. Wow, 372. That's Steel. Thanks so much for joining. Yes, welcome. I appreciate you coming here and saying hello and joining me today. Welcome back. You're becoming a regular here, which is fun. Where are we? Here we go. Let's get loaded up here. All right. Oh, there we go. Cool. Cool. Day 3 of 3. Yeah, you're a regular. I appreciate you coming in, connecting with me here. It's fun to have you for sure. Let's get a problem loaded up here. 322. Okay. I think we'll go to 320. We'll see. All right, we got the lava lamp loaded up. It's heating up. We got an incense burning. So we are got the mood set here to learn some programming together. High school finals. Oh, nice. How's that going? Okay, so we're on 322. So let's copy this over. All right. Z. So help get the formatting on this. Okay. So this says show that the ceiling of f of n is O of f of n if f of n is a positive non-decreasing function that will always be greater than 1. So things that we know that f of n is greater than 1. Oh, whoops. Sorry, guys. Greater than 1. Right? We know, so we want to show that the ceiling of f of n is less than or equal to some constant c1 times f of n, right? So we also know, we also are given the ceiling notation, right? So ceiling function. Let's come on. Okay, so we say that kid dude said, I spent about 2 hours today going over this chapter again, starting to get the hang of it. Awesome, that kid dude. That's really great news. Yeah, it's definitely a an hours kind of game. The more time you spend into it, especially it seems it kind of correlates to what you get out of it so far. Now that might cap at some point, but it definitely you got to just grind through some hours thinking about it and everything. Welcome. I appreciate you joining. Thanks so much for coming today again. You guys are awesome. You guys are really okay. So let's go here and let's say um, so what is the if I have ceiling f of n function. So we know, come on, this is not what I'm wanting. Um, okay, we'll just take the prompt. We'll say, don't tell me the answer. Let's go step by step. I need that equation. The book doesn't give us this equation for some reason. Got to back this up. It's a little strong. Barely breathe over here. Okay. Great. Let's go see step by step. Restate what we need to prove. Show that. So we have these two things, right? So we need to understand this right here. So the ceiling function rounds f of n up to the nearest integer. So for any real number f of n, we have this. Okay, so this is what I was looking for. So f of n is less than or equal to, right, the ceiling of f of n, right, because it's going to be rounded up, which it will be less than, unless, so if f of n is like 1.7, it'll be rounded up to 2, which will be f of n ceiling. If f of n is already 2, well, that is equal to the f of n ceiling. So it's already in that case, right? So, which it'll be less than or equal to f of n plus 1, right? Because the next ceiling up would be f of n plus 1. Okay, so then so we know that f of n, so understand the relationship between the ceiling of f of n and f of n. The ceiling function rounds f of n up to the nearest integer, so any real number f of n we have, right. Thus we can say f of n, the ceiling is less than or equal to f of n plus 1. So how did they get to here? This from this to this? They just dropped this function here, or they combined this, but they kept it less than or equal to. How did you rearrange that function? So I simply use the relationship. So now applying this to f of n, we use some real numbers, which are some real numbers. We will simply use relationship between f of n and the ceiling f of n to establish that. This helps us create the upper bound, but that doesn't tell me how they just got over to this. They just brought this inequality over to here. So the ceiling is less than or equal to f of n plus 1. So the ceiling is less than or equal to. So if the number is like 2.1, let's just go like 0.1, or let's do like 0.5. So 0.5 would get rounded up to 1. 0.5 plus 1 would be 1.5. So that is true. Right, okay. So it's weird that they. So then this becomes less than or equal to f of n plus 1. Okay. So now this is some, we have the ceiling is, now we have, right, now we have some constant out here. This matches the big O equal. Right? So now we can, what we can do is we can add C back in, right? So right here, C would go right here. Some constant C times f of n plus 1. So now we can add some constant C into the equation to match a big O. Okay. So the goal is to show this. So from the inequality, we can see that we can rearrange this inequality to, but how did they get to this? So we're f of n plus 1 what? Where are they getting this stuff from? Okay. Right, so we have f of n, ceiling of f of n is less than or equal to some constant c1 times f of n plus 1. We can rewrite this as ceiling of s. What? No, the GPT is not making any sense right here. I don't know what it's saying. Let's get rid of that crap. Okay, so some function, so f of n is greater than 1. We have this inequality here that shows that that's true. So then what can we do? We can say f of n, so if the f of n is equal to this, we can place this here. That kid dude said, just to let you know, there are 2 GitHub repos with solutions to some of these chapters. Oh, like from the already. What do you mean? What do you mean by there's already some, or are they by the authors or by other people? So if we plug in f of n right here for this part here, we would get this function, big O, right here, boom, like that. So then if we were to, what can we do here? You're on the right track, but let's clarify a bit to ensure everything is structured. So where f of n is positive, non-decreasing function that is always greater than 1. Let's go step by step, restating the goal. We want to prove that the ceiling of f of n is less than or equal to some constant times our function of n. For some constant c1 and a sufficiently large n. So we know that the relationship between the ceiling and f of n is this statement here. This tells us that the ceiling of f of n is always greater than or equal to the function of n, but less than f of n plus 1, creating the upper bound for the ceiling of f of n. We now want to prove that the ceiling of f of n is bounded above by some constant multiple of f of n from the inequality. Got you. We can focus on the right-hand side, which gives us this part. See, I don't know how they had a less than or equal to, they have a less than, but now they have a less than or equal to here. F of n plus 1 would not be the ceiling. How can you add in a equal, listen, when if plus 1 when it was less than 1. The original inequality is this. This means that f of n is less than or equal to, which is true because the ceiling rounds up, which is true because it's always less than greater than f of n, okay? The inequality doesn't allow us to replace less than symbol with a less than or equal to directly. That would be a misstep. However, here's what we can do with this inequality. Right bound adjustment. We know that the upper, or the ceiling of f of n is strictly less than f of n plus 1, so it's bounded by f of n plus 1, not exactly f of n plus 1, so it's less than that. Upper bound of big O. To prove that O of f of n, we want to show that the ceiling of f of n is less than or equal to some constant multiple of f of n. You don't replace with, but you use the inequality. This is doing a really terrible job of explaining this. And really, it's doing a really bad job. So let's go back to the drawing board here. So if we are at this statement here, where we have the inequality at this point, what we can do is we can divide, I think, by f of n. I think I've seen that done before. We can divide, let's copy this down. We'll say divide by f of n. Okay. So this will become 1 is less than or equal to f of n, the ceiling divided by f of n of 1 plus 1 over f of n, right? Okay, So this tells us so what if we take this part now and plug it into this? Yes, you're absolutely right. Let's break down and carefully understand each part of the inequality. So if we divide by n, we get what we have here, right? Exactly. Explanation. The left part gives us 1, the lower bound of the fraction, which is clearly 1. The right part gives us, which simplifies to this, so the inequality is written as this. Shows the ratio of the ceiling of fn to f of n. This tells us the ratio is bound between 1 and a value slightly larger than 1, with the skipping of f of n go as this, with this gap shrinking as f of n grows. Why is this useful? For large n or large f of n, the term 1 over f of n becomes very small, so the ratio of the ceiling to f of n of f over f of n approaches 1. This is key, showing that so if f of n becomes very large, right, this just becomes like more asymptotic, right? Exactly. Meaning that we just slowly start to increase our bounding. Okay, yeah. So how can I finish the proof from here? BG says, cool to see the YouTube algo throw you my way, Michael. I'm about to get started with streaming as a beginner doing Linux, networking, some coding / scripting. Best of luck with everything. Well, thanks so much, BG, for stopping in. I appreciate you, and good luck with your stream and everything. That sounds great. And, good luck with your learning, and thanks so much for stopping in here and saying hello. It's good to meet you. And for following along here. Okay, so you're almost there. Now that we have the inequality, let's finish the proof step by step. We want to show that O of f is f of n, right? We use the bound that we have here, our equality. We multiply through f of n. So we're going to multiply f of n back through in this stage. Weird. So multiply f of n out of the denominator. So this would give us f of n is less than or equal to the ceiling of f of n divided by 1 or they have f of n out front here times 1 plus 1. Oh god. Like that, yeah. One more parenthesis. Here we go. Let's get some caught up on the chat here. That still says, where do you learn Linux? Are you taking networking by CompTIA? Jeremy says, how's it going, Mike? How's it going, Jeremy? Appreciate you coming in. Muna says, how's it going? Hello, Muna. Thank you for coming in today. Good to see you. Cool. Okay, so now simplifying the right-hand side becomes, if we multiply the f of n, we get f of n times, so this becomes f of n. So we will simplify the right side. So this becomes, if we multiply the f of n through, this becomes f of n, and then this becomes plus 1. Right? That's the simplified on the right-hand side here. And so now we need to find a constant 1. Find a constant now to prove that the ceiling of f of n of o is O of f of n. I'm going to show them what. Oh my god. We want to show that for sufficiently large n, we can find a constant c1 such that, right? Boom. From the inequality, we know that we're back at this stage. We need to ensure that we can be bounded by some constant of f of n for large n. F of n plus 1 behaves very similarly to f of n. So we can rewrite this as f of n plus 1 is less than or equal to 2 times f of n. We need to ensure that this can be bounded by a constant multiple of f of n. For large n, f of n plus 1 behaves very similar to f of n. So we can write, okay, so we just swap in f of n into here, or this part of the equation into this one, because it behaves very similarly. And then they add in some constant here times f of n. They plug this into our equation here. Okay, so what we have now is we have this function here, and it gets brought into, it becomes this, right? Because it's less than or equal to f of n. From the inequality, we know that. How do we know that? Why do we know that? The ceiling okay. So we will, now what we'll do is use in our big O inequality, right? So we'll plug this into our big O inequality as this, which resembles f of n for sufficiently large n, is less than or equal to some constant c1 times f of n, right? And then we will say pick some constant why did you pick c equals 2? Good question. Let me explain why we picked c equals 2. The goal of the proof is to show that the ceiling of f of n is O of f of n, which means that we first need to find some constant c1 such that to make this true. Recap. We know that blah, 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 blah. Now our task is to show that the ceiling of f of n is also bounded above by some constant multiple of f of n. To do this, we want to rewrite f of n plus 1 in a way to show it's less than or equal to some multiple of f of n. Why is c1 equals 2? The expression f of n plus 1 grows more slowly than 2 times f of n, but for large enough f of n plus large enough n, f of n plus 1 is always less than or equal to 2 times f of n. Here's why. For any f of n greater than we have, this ChatGPT is pretty bad at explaining this one. I'm not gonna lie, guys. I'm sorry. I'm not really understanding this one that well. ChatGPT sucks for this one too. So Well, this basically is in our notation for big O, right? So f of n is always greater than 1, so 2, 2 plus 3, 3, this is 2, 2 times some constant. So we have to be greater than 1, right? So 2 times, interesting. Um, let's get caught up in the chat here, guys. Sorry. We got a lot of chats. Oh, my bad, guys. I started studying CCNA a few days ago. I'm interested in networks and seems like a challenge. I'm planning on doing security plus on the summer after I get off an entry level tech job while freshman in college. It's a lot easier to network plus. Just my opinion. Okay, how viable do you think that? Okay, you guys are just talking amongst yourself. Hey, little Timmy, thanks so much for joining. I appreciate you coming in and leaving a comment. Hello. Um. Okay, just more chats amongst yourselves. Okay, so this is basically the answer here, so I'm gonna move on. This problem sucked really bad. Hey, that kid, dude, can you link me? Do they have a solution to 322 in chapter 3? The 20 problem 23.22. If they have one, can you link it to me? I would appreciate it. Okay, let's go move on here to this one. Give a big O characterization in terms of n for the running time in example 1 in code fragment 3.10. Okay, it's right here. Okay, so we have to give a big O characterization in terms of n of the running time of example 1 shown in code fragment 3.10. Code fragment. Okay, here it is. This is code fragment 3.1. So I'm gonna. All right. Um, that steel dude says try going to Math GPT. It's way better for coding. Okay. What school are you going to? Playing it? One sec. I'll link you. Hey Sam, I appreciate you coming in, joining. Thank you so much for leaving a comment. And yeah, we're just studying some data structures and algorithms in Python right now. We got some regulars chatting it up right now, talking. So yeah, thanks so much for joining, and feel free to join the conversation and learn away with me here. Yes, and the channel's been growing real rapidly, you guys. Thank you so much for all the support. I really need to make some more Python crash course videos to go over this try it yourself problems in Python crash course, and I need to um, make a demo video for the task tracker project we made. But I just between the streams and work, I've been busy, busy. Okay, code fragment 3.1. We need to give a big O characterization in terms of n of the running time. Okay, so this one we're going to find max. We initially have a constant time function. We have a for loop where we access every value in the data point. We do a comparison. So this is going to have a big big O of n time, right? We have so I'll say, we'll make a little bit of more notation here. Say, we'll say def find max, which takes in data, right? Biggest is equal to data at index 0. So this is a constant time. This is in constant time. We have for val in data. If val greater than data, or biggest, sorry, we're going to make biggest is equal to val. And then we're going to return biggest at the end, right? So this is going to be a looping through every value of data or n. This is a comparison, so this is a comparison constant time. So this is a linear time. This is a variable declaration, which is a constant time function. And then a return, a constant time. All right. Yeah, as many seem nice, seems like a good plan. Dat still says 1K in the next month. Hopefully, that'd be so cool if we hit 1K. Brittany Folk, thanks so much for joining the stream. I appreciate you coming in today. Right now we're doing data structures and algorithms Python, doing some practice problems at the end of chapter 3 where we learned about big O notation and some critical functions for determining big O, big omega, and thus big theta. And yeah, so we've been going through some practice problems as you can see in chapter 3, and we're almost getting done there. And then, I do not know any other languages besides Python. I know a little bit of like basic HTML and CSS, but I really am focusing on getting a solid and very secure understanding and fluent, ability in Python before I move on. I have a theory that I think it might be. I think a lot of computer scientists today like to spread out their knowledge amongst so many languages to try and cover all the bases, where maybe they could be better served by specializing in just a few of them extremely well, and then if they need to expand outwards from there. So and plus a lot of the languages do what they all kind of mimic one another in certain ways. Obviously not, some people might disagree, but you can do most things in any of them, right? Besides, obviously some have certain specialties, but I'll stop talking. I'm probably getting ahead of myself. But no, I just am really interested in Python right now. I think it serves all the purposes I need for at the moment. And, we're just cracking the surface really of what we can get started. If I were to move on right now, I feel like I'd be doing myself a disservice because I'm just now starting to, that's like, taking Spanish class in high school for 2 years and then never speaking it again. It was kind of like a waste, right? I forgot everything in Spanish. So, no, it's not exactly one to one, but it's kind of an analogy I like to use. So, yeah, I'm gonna just keep going until I really won't forget any of this, until I'm kind of have a mastery or whatever in it, and whatever that means. So, all right. Um, that kid dude. I don't see the link in chat. I don't think links are allowed in the chat, unfortunately. So, do you mind if you're in the Discord, just shoot it in the Discord and I'll check it out from there. Now that I think of it, let me remind you of another person. I believe I studied organic chemistry in graduate school. They're now a synthetic chemist at a pharma company. Awesome. That's really cool. Yeah, they organic chemistry was a pretty tough course. I did very well in it, but I don't remember a lot because I haven't had to apply it. But I remember a lot of my physical chemistry. I was a TA and a lab instructor for that course for those courses, and so I know those pretty well. Like, but my organic is pretty rusty. uh, Muna says they've also been learning Python, hoping to use it in their field. Oh, that's really awesome. You should, show them the stream. Maybe we could connect. We have that in common, so it would be good to have them join the community. Brittany says, I'm trying to learn C++ for my first language. Do you think I should switch over to Python? I can't really tell you. I don't want to, steer you in a direction one way or the other. If you already are learning one thing and you feel comfortable continuing, I don't know, maybe it wouldn't make sense to stop right now, but if you're just getting started, I personally am learning Python. There's just abundant amount of resources on it. It covers all the things I need. I'm a scientist, so I like data and information, so Python can do all that. I can make these, applications. I can do a lot of things, and so I that's why I'm sticking with it for now. And but I don't know. Anyone have any other opinions? I know some other people in here might know C++. Maybe like Jeremy and them. Okay, so I think that this function would just be an O of n time. So I'm gonna copy this into here. Boom. The function find max in the function iterates through each element of the data list once, comparing each value to the current's biggest value and updates the biggest if necessary. Here's a breakdown. A constant time. This loop, all elements, iteration involves a O of 1, O of 1, O of 1. So it run an O of n time. Yep, cool. So find max equals O of n time. Cool. That is that problem. Okay, now we're moving here. We're moving here, boys and gals. We have some gals in here. Thank you so much for joining, everybody. Appreciate you guys spending some time with me out of your day. I know that learning Python on a Wednesday night isn't everybody's cup of tea, but hey, we're grinding here, trying to get better ourselves through any possible skill sets, really. So, good on us, and we'll getting through this. Okay, so let's go back up here. 320. Oh, shoot. Code fragment 3.1. Example 2? What? Code fragment 3.1. 0. Oh, shoot. I'm an idiot. Sorry, guys. Wrong function. Wrong function. Oh, gosh. Okay, let's quickly copy these over. My bad, you guys. I have led us astray. So this guy, paste that here, delete, take this, go here, take this, delete, return total. Okay, here we go. We're back in business. We got some chats here. Thank you guys for being active in the chat. You make this a lot more enjoyable and interactive. It's so awesome. Um, Dat Steel said, I learned C++ first, not enough resources, and it was hard. Wouldn't recommend personally. Okay, I'll think about it. That's what all you can do with Python. You can basically do anything with Python. I've been teaching myself for the past month and created a few games posted on GitHub. The link is off topic channel. Okay, I'll check that out, that kid. Thank you. Yeah, Python is it's pretty limited to your own creativity. It has all these functions and various third-party packages. There's a lot of third-party packages and modules that other programmers have wrote and implemented, and so it's really you can do any you can create games in it. You can do data analysis, machine learning. You can make web apps in it. You can do anything in it really. So it's from my understanding. Okay, so we have example one, which takes in some sequence. We take a length. So a length is a function which is in constant time. We have a total, so this is a constant time. Right, we have a loop over every value in the range of n. In the range of n. We add total of sequence. So this would be linear time. This right here is constant time. So this would be O of n. Like that. Okay, so the initialization, taking the length is O of 1, setting a variable is O of 1, loops through all n elements from the list of s aside of the loop, um, inside of the loop, addition, O of 1, return O of 1 since the loop runs n times for each iteration perform of a constant operation. The overall time complexity is O of n, just like we said. Gotcha. Cool. Moving on. All right. Example 2. Okay, so then we'll take these. Go in, go in, go in, go in one. There we go. Like that. Cool. Um, what's going on here? There we go. Okay, so now let's go through this function here. Example 2. So we have this is in constant time, right? This is in constant time. For j in range of 0 to n with a skip of 2, increment of 2. So this would be in we're skipping 2 every time. So this would be O of n divided by 2. Now it's not a log because we're not going, skipping, dividing further after every iteration. I think it's just a linear O of n divided by 2, which would be just O of n. So this is linear time, and this is constant time, and then this is also a constant time. Anybody have any disagreements? Is this would still be linear time? It would just be n divided by 2, um, right? Let's go find out. Magic orb, tell me the answers. Starting into each time. This means the loop runs for n divided by 2 times. In terms of complexity, it's still linear with respect to the element's s for every second element, so it runs an O of n time. Boom, we are correct. Sweet. Good job, guys. All right, moving on to the next problem. R3.25 underscore key dot pi. We're going to take this guy here. Paste him here. Take out this guy. Okay. Okay, cool. Like this. All right, so in this example, well, hold on. We need to see if we're actually doing the right problem here. 325. Example 3, we go to example 5. Okay, we're going to go all the way to example 5. Hey guys, which peanut butter do you recommend for spreading? Chill. Caught me off guard. Had me in the first half there, I'm not gonna lie. Had me in the first half. It's off topic. Oh, you're talking about the above comment. That's funny, Dad. Talking about that kid's comment. I posted something on the off topic by chance. Just check it out if you get a second. It's like, yeah, which peanut butter? That's funny. Okay, so we have this is going to be constant time. This is also going to be constant time. We have a for j in the range of n, so we're iterating through all of n values. So this is going to be linear time. But we also have another loop that goes for j. We increment 1 for j every time. So this is going to be linear, but deep, we'll say like deep linear. I don't know how else to really say it. Like this does an iteration over ends, and then this is constant, and then this is constant. Okay, so nested linear, we'll say nested. So then this function would overall O of n squared. Contains a nested for loop that impacts its time complexity. Here's the breakdown. Initialization 0, setting the total to 0 is a constant time operation. Outer loop j For j in range n, the outer loop runs for n iterations. The inner loop for k in range 1 plus j. For each iteration over the outer loop where j ranges from 0 to n minus 1, the inner loop runs j plus 1 times for each. For example, when j equals 0, the outer loop runs j equals 1. So this runs twice and so on. In total, the inner loop runs, but yada yada yada. This means the inner loop runs for a total of 1 plus 3 plus 2 all the way to n, which is the sum of the integers, which simplifies to O of n squared. Cool. We were right. So this should be O of n times j. Yeah, right. Okay, so that would make sense. Is this not O of n times j? Great question. Let's take a closer look at time complexity example 3. You mentioned O of n j, which is an understandable thought, but this isn't the correct characterization in this case. The term j is the inner loop. Its range is not a fixed factor. Rather, it increases with each iteration of the outer loop. So the number of iterations in the inner loop depends on j, which leads to a cumulative sum iteration for the overall values, resulting in n squared, O of n squared, not O of n times j. Yeah, interesting. Hey Anthony. Anthony just comes in here. He's kind of like a sleeper. He just he pops in. He like will comment at like the hour mark out of nowhere. What's up, Anthony? I appreciate you coming in again. Okay, so let's do the next problem here. R 3.26 underscore key dot pi. 326. Oh boy, where was all those examples? Read a lot on stream. My gosh, this chapter. I think it was right here. Where is it? I can't find it. 3.10. Oh my gosh. Example 4. There we go. All right, let's copy this over. Get this in here. My dog is growling at the neighbors. Don't mind her. She's just being grumpy. Quit being grumpy. She's the my dog is the header of my channel, like the header picture. All right. Boom, 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 boom. Boom. Okay. Okay, so this one we have a this is going to be constant. This is going to be constant. This is going to be what is range n? Oh, we're missing a variable here. Prefix n equals length s. There we go. Okay. So for j, so this is going to be linear. This is going to be constant. And then And this is going to be constant as well. As well as this. So this is going to have an overall time complexity of O of n. Let's give this a check. Oh, whoops. Oh, whoops. What the heck? There we go. The overall time complexity, oh, wait, hold on. Example 4, okay, O of 1, O of 1, time complexity, O of n. Yep, we were right. Cool. Nice. All right, let's go ahead and we got one more example here. R 3.27 key.pi. Okay, we're going to take example 5 here. Boom. Take that guy. We're gonna take this whole line out. Take this guy out, tab it in. Take this guy out, tab it in. Oop. Tab, tabs, tab. Take this out, take this out. Take all this crap out. Sorry guys, a lot of reformatting here, my bad. Just trying to get it all copied over here. There we go. Okay, so now if we go over this, we have, this is going to be constant time. This is also going to be constant time for I in the range of n, total equals 0. So this is going to be linear time where we're iterating over every range value of n of 0 to 1, n minus 1. We are so we are going to, this is a sorry, constant here. Oh, these are nested. For J. Is this right? It's supposed to be under the 4, which is under the total of 4. Count n. Yeah, this is the right setup here. Hey, Gina. Hello. How was dance? Hey, Jax. Yeah, my bad. It's n squared. Long day. Yeah, no worries. Me too. Long day today. Yeah. Hey, Ozzy. Thanks for stopping in. I appreciate you coming in. So we have something, an error going on. Unexpected indent going on here. It needs to be here. Oh no, we're missing a line. That's why. Here. There we go. Okay, so this is constant. For J in range. So this is going to be nested. A nested linear. This is also going to iterate over some values of 1 plus j. So this is going to be a nested linear. This is a constant. This equals constant. This equals constant. This equals constant. So this is going to be example 5 is going to be O of n cubed. Right, we have a linear for loop going on here. We have another linear for loop which is nested, and we have a tertiary for loop that is nested, taking in some values again. That. Let's analyze the time complexity of example 5. Length A, O of 1, count O of 1. This runs an n times, right? Middle loop, also n times. Runs in 1 plus j, increasing linear with j. Outer loop runs in. Total time complexity is O of n cubed. Oh, interesting though. So it's interesting that they bring up that this is n squared times n. Why is it n squared? The inner loop runs for a total of iterations the sum of n integers. The sum of n integers is always n squared. Therefore, for each iteration of the outer loop, the total number of operations performed on the inner loop is O of n squared. The outer loop runs n times, it's nested. The outer loop runs n times, and for each iteration of the outer loop, the nested loops perform O of n squared work. This leads to a total complexity of O of n cubed. Okay. Interesting. All right. Cool. That took care of that problem. Take. Okay. So that was 325, 327. Okay. So then 328 wants us to, or we need to copy over the question real quick. Awesome. Okay, so then that we have all the questions over. 3, 2, 1. Yep. Sounds good. Okay, nice. Hello, those that are watching. I appreciate you joining me today. If you're new here, the channel's been growing. I appreciate you joining. My name is Michael. I'm a college graduate. I have a Bachelor of Science in Human Biology and a minor in Chemistry. I focus primarily on the chemistry aspect of human physiology and biology on like a cellular level. I then got a job as a formulation chemist for a biotech company out of college, and I've been working there for about 3 years. I graduated at the end of 2021, and I started work at 2022. In my work, I often have a lot of instances where you do a lot of chemical matrices and calculations by hand, and that sparked the overall, thought of, wow, I wish I had a computer that could do this for me. And just by having that thought and that light bulb, just started this whole pathway of I, looked into what languages I want to learn. I decided on Python, and I took the Harvard CS50P course offered online through EDX. I completed that course over the summer of 2024, so June, July, and August. In August, I submitted my final project, which was a intuitive, object-oriented inventory storage system for chemicals or really whatever you wanted to store in there and label under your own circumstances. I then started the channel and started streaming all of my progress and all of my study sessions, like today. And for anybody else that was in a similar situation, and I've been reading, various textbooks to further solidify my knowledge and just increase my understanding, and then help myself make more projects. So read aloud already on the stream all of part one of Python Crash Course, which is all of just the part one is the understanding and learning of Python, and part two is projects and implementation. But we read all of part one aloud, audiobook style, just like we're doing with data structures and algorithms. We break down the snippets that we don't understand. We make sure that we understand them before we move on, and we do all the practice problems inside. And yeah, so this was a great one to help solidify those CS50P concepts. We also are right now we're doing the data structures and algorithms. After that, we'll jump into Fluent Python, which is a great book for just getting into that intermediate to advanced Python understanding, which is kind of where we're circling in on, kind of transitioning into. And then we will jump into Python machine learning for more specialty learning in the modern age and things like that. Yeah, so if that's something that interests you, please follow along the channel. I also provide all of those resources that I just mentioned, and along with all of my personal resources associated with them, such as my notes, maybe some videos, like stuff on the channel, obviously. Other just like how-tos, where to get started, like flow, basically how I started, what you can do, links, things like that. I created a Discord link below where it's just a conglomeration or a compilation of all of my resources for everybody on the stream to gain access, and also to chat offline and have a conversation and community there as well. So if that's something you're interested in, please follow that. But let's go ahead, and we are almost done with these problems. We only have a couple more. So I think I want to get to 30 and then stop there, and then leave the last four for tomorrow, and then we will move on to chapter 4 after that. And so we'll start diving into, I bet you it's going to start actually writing, teaching us different types of algorithms, like we already have the functions associated with them, right, for classifying, but then we're actually going to learn the algorithms that are being used out there in society currently. So we're going to get into that quickly here, and probably data structures, especially we're going to get into probably memory allocation right now. So we talked about time allocation, and but then we're probably going to get into memory as well, which in Python we haven't really had to keep track of, but we're going to need to keep that in mind. So 328 says, for each function f of n and time t in the following table, determine the largest n of a problem p that can be solved in time t if the algorithm largest n of problem p can be solved in time t. Wait, hold on. Determine the largest size n of problem p that can be solved in time t if the algorithm of solving p tasks f of n. Oh, if the problem of solving p takes f of n microseconds. One entry is already completed. So 1 second for each function and time. So we have a function and we have time. Determine the largest n size of a problem that can be solved in this. Okay, so this is not that hard. Let's just go to Desmos. Let's just plot these guys. Right, we'll say f of n. And then what we're going to say is y equals the size that can be solved if it takes function microseconds. Determine the largest size of n a problem p can be solved in time t if the algorithm for solving p takes f of n microseconds. So 10 to the power of in 1 second for log n. That would give us the x input. So if I go x is equal to 10 to the power of 1 300,000, it's just gonna be huge. There's just no way, right? Yeah, there's no way. Whoa, shoot. Scale in here. Ooh. So how could we then solve this mathematically? So the thing I'm not getting is the this part here can be solved in time t if the algorithm for solving p takes function of n microseconds. Gosh. Let's go. Ooh. R 3.28 for keyed up high. Okay. We're gonna take this guy over here. Paste it here. What happens if I tried it? No, so it's not gonna work. How can we go about solving this one? So if you put in Desmos, if you put in log of 10, log base 2, right, of 10 to the power of 300,000, just undefined. This is so big. Anybody have any ideas? Survey says. Okay, determine the largest size of n for a problem p that can be solved in t time. If the algorithm for solving p takes f of n microseconds. For each function f of n. How did it do this? If the algorithm for solving p takes f of n microseconds. So log n microseconds. Whatever that is. I'm not sure. Gotta go to the orb, everybody. So to solve the problem, you need to determine the largest size n of problem p that can be solved in a given amount of t based on the time complexity of f of n of the algorithm. Here's a step-by-step approach to start with the time complexity of the function. It represents the number of microseconds the algorithm takes to solve a problem the size of n. Determine the largest n given time t in microseconds. You want to find the largest n such that f of n is less than or equal to t. This can be solved by rearranging the time complexity solved for n. Okay. So what they suggest we do is we know that determine the largest n. So for function of n is less than or equal to t, right? We can take the solve for n. This will depend on the function f of n, for example. Okay, so in the case of n or log of n is less than or equal to t, if t is 1 hour, or what is 1 hour in microseconds? 1 million microseconds. No. 3.6 billion microseconds. Three, 6, right? Which is 1 hour. Okay. Then we would just do, so this says, all this says is 2 to the power of what n value is less than or equal to this, right? So we would need to how do you remove an exponent? You could obviously take the square root of n, but we don't know what n is in this case. Okay, so how can I remove n out of an exponent? Use natural log. I can natural log both sides. So then if I did that, that would be n times the natural log of 2 is less than or equal to the natural log of this guy. Right? So what would that be in this case? So then you would just divide by natural log of 2. To give you n. Okay, what would that be? I don't know if I'm doing this right, but we'll find out here. Natural log 3, 6, 1, 2, 1, 2, 3, 4, 5, 6 divided by natural log of 2. 31.7. Really? There's no way. 31.7? What? In 1 hour? Oh my gosh. What is going on? So for every function of f of n, so we have f of n and the time t, determine the larger size n if the function takes microseconds. So let's go back to the Jeopardy and say um, log n and 1 hour. To remove the logarithm, rewrite the equation with the exponential form. Log n what? Log base 10? Solve for n? What did I do wrong here? So they didn't take any natural, they did. Am I not using log base 2? They look like they're using log base 10 though. Why are they using log base 10? Do log n and 1 second. Okay, so they are using log base 10 for here for some reason. It looks like you're trying to relate different time complexities to time durations. Logarithms likely log base 10 to express the values. Yeah, why is it? It's weird that they're using a log base 10 here, right? They said that they would only use log base 2 unless otherwise stated. They didn't state anything saying log base 10. How am I supposed to know that? They have a base 2 here for the exponential function. That's kind of annoying. So then if you take this guy, paste it in here. Ten to the power of 6. Yeah, this is strange. What? Does anybody know what this is trying to get us at here? So then what do we say? How many are in a second? 1,000 milliseconds in a second. So why is log for 1 second 10 to the power of 300,000 for input? Oh, this is sorry, not milliseconds, microseconds. A million. So if you can compute log n, let's try to prove the first one, right? So you have log n is less than or equal to a million microseconds, or 1 second, right? This becomes 2 to the power of what value is less than or equal to a million? So we need to be able to divide n by a million. N divided by 2 a million times. What? So log n is less than or equal to 1 million microseconds. So let's take this, put it here. What does it say here? 10 to the million. So why does that have 10 to the 300,000 here? We have that right here. For each f of n. So we have f of n is log n here is less than or equal to a million for microseconds. For 1 second, you have a million microseconds. So you should be at 2 to the power of, what was 2 to the power of a million. Is that the same as 10 to the power of 300,000? No. So, what's going on here? For each function and time in the following table, determine the largest n of a problem that can be solved in the time of the algorithm. For solving p, if the algorithm for solving p takes f of n microseconds, oh, hold on. So f of n microseconds, so log, let's try this. Let's see what happens if we put in the log of 10 to the power of 300,000. Log base 2, 10. Oh, come on. Gives me undefined. F of n. No. Yeah, I'm not. This is. Yeah, I don't get. I cannot replicate this answer. It gave us one of the answers for us, but I cannot get it again. So let me take this. I'll paste it into the Jippity. We'll say boom. Okay. Say log n and 1 second. To find the largest n value, 2 to the power of a million. I got this. Okay, so these numbers are the same in base 10 logarithms? So it'd be 2.1 million times 0.301, which is log base 10 times 2. What? 2 to the power of 1 million is equal to... Stop your growling, knock it off. You're alright. It's just the neighbors. So log base 10 times 2 is 3.010. Log base 10 times 2. Why are they doing log base 10 times 2? To convert it from base 10 to base 2? So then, okay. So what would happen? Come on. What would happen if we go if we do log Oh, this one's really annoying. I just do not want to do this one. Should we just save it for tomorrow? This is crap. For real, this is annoying. Okay, so what about 1 hour? For 1 hour, we need to determine the largest n such that the logarithm with time complexity log n can run in 1 hour. Convert 1 hour to microseconds is 3.6 billion microseconds. Set up the inequality. Log base 2 then is 2 to the power of 3.6 billion. This represents an extremely large number. We can approximate it by converting to log base 10. So to convert it to log base 10, you just take log base 10 and then you use for your input value, you use the base of what you're converting from. Interesting. So it'd be 10 to the power of 1.083 1 billion. Jeez Louise. Um, okay, so let's do it like this, guys. Get a drink here. All right, cool. So we'll say log n. Nolan Nozik says, "Why are you learning like this? You don't think it'll be better and easier for you to learn and work on something as you learn as you go?" No, that's a great question. No worries. I'll answer that for you. So in the welcome to my stream. I appreciate you joining here. But in the first half of my stream, we take on new learning. It is critical and essential that we take on new learning. All of this stuff would be taught in a college lecture. This is a college level textbook going over data structures and algorithms. So all of this stuff is what is being taught in current computer science courses. So we this stuff is critical for knowing in the field. But we do in the back half of our streams, typically, I'm not sure if we're going to get to it today because I'm kind of grinding through these. I want to get done. We're almost done with these. We only have to get to 34, and then we can move on to chapter 4. I'm not. I only do the reinforcement problems. I don't do the creativity or project problems. So we're almost done. So I was just trying to push through here to hopefully get down to chapter 4 and get into reading. But in the back half of my streams and on the weekends, especially as we work on personal projects that we're building, and right now on stream, we've already built a task tracker project, which is completely object oriented and is up on our GitHub right now. And then right now we're making a small business manager where we have items or items which can be converted to for sale items and then converted to sold items. We're writing a script to overall kind of manage the flow and UI here in a CLI interface, terminal interface, and we have saving file saving going on, reading and writing. We also have this other mode class that we're gonna create where this the mode is the like shipping or method of the sold items. So we've been creating this. So yeah, we do have a critical or a large portion of this channel is creating projects live on stream, but you can't avoid learning the new concepts to then implement them into the project. So eventually, in this project we're working on in that small business manager, we're going to need to be able to filter, access, and sort mass amounts of items in a business catalog or a business's catalog. So we're going to be implementing these functions from this book directly into our work here, and so it's all stepping on one another. So no, thank you for your question. Appreciate you stopping in. All right. Okay, so let's go. Let's do it like this. We'll go over like so. We'll make this 1 second. We'll go over. Make this 1 hour. Go over. Make this 1 month. Go over. Make this 1 century. Yeah, Nolan, if you're interested in, thanks so much for following along. And if this is something that interests you, please do follow along. And, I love interacting with you guys. And I build these projects like the small business manager. I'll pull up the task tracker here. This is one we've already pushed and published to GitHub, and it's currently live. So we have a task tracker application. If I go ahead and just run it really fast, that can take in data, reads expired tasks that were pre-existing in the file that expired the previous day. You can uh, add new ones, right? You can assign them days to complete in the future. You can view them. They'll have associated days. Those get updated. You can filter for priority, right? So, anyways, if you can definitely, I have tons of demonstrations. I'm going to be publishing a demo video of this project. We completed it about a month ago, so fairly recently. But I'm just gonna clear that so I don't have to override my file here because I want to use these expired tasks in um, my demo video. But yeah, we have this whole project set up already, and so we do, it's not just grinding away on books and text. We do actually implement and put this stuff and our money where our mouth is. We, at least we try to. So this is going to be about 10 to the power of 300,000. Okay, like so. 1 hour is going to be about 10 to the power of so let's do the math here. If we have log base 2 to some value of n is less than or equal to 3 6 0 0 0 0 0 0 0 0, right? This essentially is the same as saying n to the power, or 2 to the some value of, to the power of some value of n is equal to this. Now, what is that? I'm not sure exactly. How do we solve that? So you would just take your and swap places with n. 2 to the power. I'm going to take this, say, break this down. Lesson 2. To remove the logarithm, we need to rewrite the inequality in exponential form. Since log 2 n is logarithm of 2 of n in base 2, we can reverse the logarithm operation, raising 2 to both sides of the inequality. Okay, so if you raise both sides of the inequality by 2, you cancel out the log base and leave n, and then have 2 to the power of the value on the other side. Okay. So this will be 2 to the power of this guy, right, is equal to n. It's less than, greater than or equal to n. Right, like so. So then what is this exactly? This is here. So now we need to convert this to log base 10. And we do so by just multiplying in the top of the expression here, in the exponent. We would multiply the exponent by, oh gosh, log base 10 2. Like that, right? Which would give us undefined. Can I force it to give me a value here? We'll leave and go. We'll give it to Jippity and say. Give me the answer to. Okay. Is too large for a standard computational tool to handle directly to sheer size of the value. It's incredibly large that exceeds limits of typical data types and systems. However, as previously calculated, the logarithm conversion tells us that this value is approximately 10 to the power of 1,083,600,000, which is much easier to comprehend since it's expressed as a power of 10. So how do you convert? Show me conversion. Let's break down the conversion process step by step. So for log base 10 is equal to 3.301. Now we multiply that by that when it gives us this. Okay. So we'll take this value, power of 10, 1, 0, 0, 8, 3, 6, 0, 0, like that. Okay. Okay, then 1 month. Microseconds. 1 month in microseconds is going to equal a lot of microseconds. This many microseconds. So it'd be 2 to the power. So multiply that times that by, what was it, 0.301. 0.301. Give me answers inside note. Okay. Okay, so this will be 1 month will be about 10 to the power of this guy. 7.80192 to the power of, or what's 10 to the power of 11, right? Log in. Okay. This is taking forever. Okay, so Is that the correct answer? Or is 10 raised to that? Is 10 raised to that answer correct for log n and 1 hour or 1 month time? Let's break down to ensure log to end 1 month is correct. You previously calculated, we determined 1 month 30 days. Two times power to the no 2.3. What? Where did it get that? So I did. Oh, I have Theed. Now, does this book have a section to check your answers? No, that's why I use the Almighty Orb here. So if we do 1 month, it's gonna say 7, right? That's 1 month. 2 to the power of that. Okay, so times this value. There's 10 to the 11th. So then we need to multiply that by there to give us log base 10. So it'd be 10 to the power of 2.350. Okay. So then let's try this again. So we'll say microseconds in 1 century. Okay. So this is the amount of microseconds in 1 century. So we'll say, right, that's it's going to be 2 to the power of that. Multiply that by 0.301. So this will be 10 to the power of 9.492 times 10 to the power of 14. Okay, now let's check. Log n and 1 century. Log base 2, 2 to the power of 3 point to the power of 15 times 301, 9.492 to the power of 14. Yep, okay, cool. Oh my gosh, this is a terrible problem. This is taking forever. Sorry, you guys, this cannot be that entertaining. I appreciate you guys staying on with me here. Nolan says, what time do you normally hop on? Yeah, I get off work at around 4:30, 5:30. I usually get home around 6 or 6:30, and then I'll get on stream around 7. All right, so now we have n, right? Okay, so now we have function n, which is less than or equal to t. So we can get just the amount of time. If the function is n, then all we can get done in that amount of time is just t, is linear. It's equal to the amount of time. So for 1 second is 1,000,000 microseconds, right? It's 1,000,000. right? 1 hour would be 3.6 billion. 1 month would be 'um this many. Is 2.59 to times 10 to the power of 12. And then 1 century would be this. Why can't I just copy this one line? Why are you making me copy everything? .1536 times 10 to the power of 15. So what would if my function is n and time is 1 second, my n would be equal to time. If your function is n is linear time complex and the time available is 1 second, you can simply add the relationship. So 1 million microseconds, right? So for then it would be in 1 hour would be 3.6 billion microseconds. In 1 month, it'd be 2.59 to the power of 12, yep. And then 1 century. To the power of 15. Cool. Okay, that took care of that one. Now we need to do n log n. Oh god. So is this not going to be just these two values times each other? Now that we have done log n and n, if we want to solve the for f of n is equal to n log n, is it not just our previous values multiplied together? Yes, you're correct. The function solution. So from before, right, it's now our solution for n log n is just going to be these two multiplied, because if log n is this for 1 second and 1 hour and 1 month, and n is this, well now if we're just our function is n log n, we can just do the multiplication of these two together. So it'd be 10 to the power of 300,000 times 1 million. Do it. $306,000. Ten to the power of, so this would just be 6,000. Hey Jordan Woods, thanks so much for the comment. This is Data Structures and Algorithms in Python. It is a college level textbook. Going over obviously DSA and Python specifically. We are at the end of chapter 3. We have read all of chapter 1, 2, and 3 live aloud on stream and gone over it in depth. And we are doing the chapter 3 end of chapter practice problems here. Um, so then what would be n log n for 1 hour? Be 1 hour microseconds n log n. $26 million. So it'd just be these two things together. Ugh, ChatGPT's failing me. All right. I think we get the idea here. I'll come back and finish this one when I can do more high level math. But so the n log n is just going to be these two multiplied together, right? The n squared is just going to be the n value squared. And then the 2 is raised 2 to the power of this value, right? So it would be this guy times this guy. Right? It would be this guy running out of room here. Right. Be this guy times this guy. Right? And this one be this guy times this guy. It is 9:10 p.m. for me. Right, and then let's just do n squared. Yeah, this question was really dumb. Do not be discouraged. I did not like this one either. It was really kind of poorly written in my opinion, and by having you use such large exponent values, it just gets really annoying really fast. So do not feel discouraged. It's not your. It's trust me. So do this. It'd be this to the power of 2. It would be this to the power of 2. It'd be this to the power of 2, right? And then the 2 to the power of n function would look like this, obviously. 2 to the power of n. 2 to the power of n. 2 to the power of n. And lastly, 2 to the power of n. Okay, cool. Nice. Jordan Wood says, Are you in college for comp sci or are you just self-learning?" I am. Yeah. So I graduated back in 2021 with the Bachelor of Science in Human Biology and a minor in chemistry. I currently work as a formulation chemist at a biotech company, and so I'm just learning this to gain additional skills, challenge myself, and um, see what it brings, see what potential options and future it could bring. So yeah. Appreciate your message. And yes, the Christmas lights. And we got a lava lamp going here. We can shake that up, get it nice and bubbly. Bubbly. We are at 380 subs, you guys. Thanks so much for subscribing. We're almost to 400, which is just crazy. We're averaging like 100 a week right now, which is just insane growth for the channel. Just can't believe it. It's just really taking me off guard. I can't stop, telling my girlfriend about, like, oh, I keep gaining subs. This is crazy. So it's fun. Yeah. So, all right. So this was the end of 328. This problem, 28 sucked. Oh my gosh. So what I'm gonna do is I'm gonna copy this and see what GPT has to say about it. It probably won't like it. And log in. 1 second, 300,000, 10 to the power of 2 to the 11, 10 to the power of 1.083 million. Okay. 10 to the power of 9 to the 14. Yep. For log n is a million, 3.6 billion, 2.5 to the power of 12, 3 point to the power of 15. Yep. N log n is going to be the n values times, yep, times, cool. For n squared is going to be a million to the power of 2, 3.6 to the power of 2 to the power of 2. Yep, we did that right. And for 2 to the power of n, we did that one right as well. Okay, so we did this right. So, cool. Good job, guys. This one was a little bit long, I know. So I'm sorry that this one was long and annoying, but this one actually helped show us that once you solve for log n and n, you can solve then for these other complexities, really. So um, once you just solve for n and log n, if you can, for certain time constraints for that function, for these various functions, right? You can then, solve these other ones just from those values. You don't even need to have to do any other further proofing because, you have the associated variables needed to make these calculations, n and log n, right? All you need is n, really. Then you can calculate the log n or right, you just need these values. So you could really, in theory, if we have n here, we could have just taken our n and did the log of it, right? With the base 2 would have given us this value. So we kind of overthought this in a sense. If we start with an n, a linear time, we can just apply these other functions to n and get those associated values. So that at that end, so we could have really just taken this 1 million, plugged it into this function log, and then gotten this value. We could have taken a million, plugged it into n log n, and gotten this value. We could have taken a million, plugged it into n squared, right, and got this value. So we should have just solved initially for n, and then just um, plugged and chugged from there. So that actually is really intuitive, and I really like that we were able to deduce that information from this problem. It just showed that we were learning this somewhat. So yeah, that's really interesting. Hopefully you guys picked up on that as well, right? It's kind of like a little hack. Once you solve n, you can really solve these other time complexities at that specific time example, right? Which is really interesting. Okay, let's just read this one just so we get a preview. Algorithm A executes an O log n time computation for each time. Computation for each entry of an element n sequence. What is the worst case running time? Oh, so it's wanting us to find the omega, the big omega, and the big omega here. Okay, let's go ahead and solve it. I know we've been doing this for a while, guys. Tonight we've been doing this for over 2 hours, but you know, we are studying. This is what it takes to get this stuff solid and become, you know, really good at it. So we're doing what it takes, and yeah, I do need to copy over. I do have the prompt there. Okay, so then let's take this. An algorithm A executes in O log n time. Computation for each entry of an n element sequence. The algorithm A executes an O log n time computation for each entry of an n element sequence. What is the worst case running time? So algorithm executes in O of log n time, which means its upper bound is an O of log n. So its best case it can run is an O of log n time. No, sorry, we're reading this problem wrong. We're reading this problem wrong. This says that algorithm A executes an O log n time computation for each entry of an n element sequence. What is the worst case running time? So if it computes an O log n at each sequence, is this just not n? Is my first inclination is going to say this is n log n, right? If we do a log n computation at each entry of a sequence, well, if we're going through the entire sequence, then this is going to be an O n log n time, would it not? For each entry of an n element sequence. Yeah, that's what I said. O of n log n, right? Let's go ahead and try it out. Correct. If an algorithm executes at O log n time computation for each entry n element sequence, its worst case running time would be indeed O n log n. Woo! We are getting this, guys. This is just proof that we're starting. This is really starting to hit home here, guys. We are getting a lot of practice. 29 problems worth of practice here over like 20 pages of material. It's a lot. We're getting it here. Good job, Theed. You got that one too with me. All right, 3-3. Given an n element sequence, algorithm B chooses log n elements in S at random. Okay, given an n element sequence S, we have algorithm B that chooses elements in S that chooses log n elements at S at random and executes an O of n time calculation for each. What is the worst case running time for algorithm B? So chooses log n elements in S at random and executes an O of n time calculation for each. So it would select at random using log n. So I think this would be O of n squared. What do you guys think? Now, that's my gut feeling here, because if we have an n element sequence and we initially do a log over those elements to select one, okay, well, that's pretty fast. We selected one. Then we execute an O of n time calculation for each element that's selected, right? So we went through each element in our n sequence at random. So it would have been n log n. And executes an O of n time calculation for each. So I'm thinking we definitely have like a for loop going on here with an O of n time calculation happening at the bottom of the for loop. So that's what's making me think that we have a log, is it log n squared? Can you have a time calc computation like that, or is it O of n squared? Because log n squared would be 2 times log, so the 2 wouldn't be constant, so no. It wouldn't be log n squared because the 2 would be a constant, and it's arbitrary. So we need... Right? I think. Let's go check it out. I think this is right. We'll find out. If we're wrong, we're wrong. To determine the worst case running time of algorithm B, let's break down the problem. The sequence S has n elements. Algorithm B chooses log n elements at random. For each of these log n elements, an O of n time calculation is executed. Steps to find the running time. Number of operations. Algorithm B selects log n elements per time per operation is O of n time per calculation. So the total running time would be n log n. Dang it. Okay, so I didn't think it was going to be another n log n problem back to back. It kind of did that old like 3 C's in a row answer on me and screwed me psychologically. So what's going on here is you're selecting random elements, and then you're just doing some sort of computation to that element. Like it's not even nested in any case, which makes sense by how this is worded, right? You just select at random, you take that element, and you just do some O of n time computation to it. So it would be O of n log n. It's not nested. There's nothing nesting going on here. We were wrong on that one, Theed. GG. GG, Theed. All right, moving on here. R3.31 underscore key dot pi. Take in 331. Given an n element sequence of integers, algorithm C executes an O of n time computation for each even number in S, and an O of log n time computation for each odd number in S. What are the best and worst case running times for algorithm C? Oh god. Okay. Well, let's think about this. So if we have a sequence of S integers, so we have like 1, 2, 3, 4, 5, algorithm C is going to take O of n time computation for each even number and an O log n time computation for each odd number. I think the best case running time, right, if there's only one sequence of integers, meaning that if there's only one, either one odd or one even, it would be, the best case would be that we start off with a value of 1 and we are given a running time of log n is the best running time. If our sequence, if sequence is equal to 1, the best case, which is the best case in my opinion, right? This would run in O of, or omega, sorry, big omega of log n, right? Because it would just return, it would just perform the log n time computation on the single odd number, right? But we're doing a time, so we're having n divided by 2 times log n, which is just n log n. So for a single odd value, it's just log n. For greater than 1 odd value, it'd be n log n. For a single even value, it would be n time. And for 2, it'd be n squared time. So think about the function. So it would say if n divided by 2. So you'd have to iterate, yeah, it'd be n squared time. So the worst case, if s is equal to 2, 4, would be worst case. And this would be big O of n squared. So an algorithm C executes O of n time computation for each even number in S. So it would say, okay, for value in S, if value modulo equals 0, then run an O of n time operation. So we'd be iterating through n divided by 2, which is O of n time, and then we'd be performing an O of n time computation for a total of 1 half times n, or 1/2 n squared. Right? So best case scenario is omega. Worst case scenario is big O. So if I go back to my notes here, big O describes the worst case scenario. Jostle, I think you got those mixed up. I wish I could stay to solve this. I need to go now. Good night. See you, man. Okay. Oh, sorry. I didn't see your bug message. Worst case is n log n. Best case is n. I think the best case would be, right? So if the best case would be where s is equal to just 1, right? The sequence is equal to 1, where you have one single odd value in there, it would take that one odd value, not have to iterate over any more n values, creating an n log n time, and just perform a log n. So you would only perform 1 log n in this case. Whereas in this case, you would have to do 1/2 n times n, which would be n squared. O of n squared. What do you guys think? I think the best case is where you have a single odd value in S and perform a single log n operation on it. The worst case would be having a list with having sequence have two odd or two even values in it. It would be 1/2 times n times n. Algorithm C executes an O of n time computation for each even number in S. So in order to access each even number in S, you have to say say for value in S, if value modulo if value modulo 2 is equal to 0, then perform O of n time computation. Then for all the values in n, do something. Yeah, that's what it would do. So it would be let's analyze carefully algorithm C and determine the best case and worst case running time. Given S has NC elements, for each even element performs O of n log. Best case. Best case happens when most of the numbers S are odd because the algorithm performs a log n time computation for each odd number. If there's only one odd number and the rest are even, you perform a log n computation for that one odd number. The best time case, since there's one odd and the rest are even, is n minus 1 even numbers. Best case. So if there's only one odd number and the rest are even. Okay, so it says integers, so I guess there can't be one value. So the best case would be one odd and like 2, 4, 6, right? So you would get omega log n. All right, hold on. Since there's one odd number and the rest are even, the time complexity for even numbers is O of n for each even number. But you only compute O of n for the even numbers, and the odd one you do O log n. Thus, the best running time is O of n for even numbers and O of log n for odd numbers, which equals O of n. So the best case running time is O of n. Okay, so the best case is big O of n because you can only perform one odd number, but you're limited by the bottlenecked by the so the worst case scenario, this is big omega of n, right? The worst case scenario um, is O of n is O of n squared. Okay, so we got the worst case right. The worst case happens every time when every even number is s is even, because the algorithm will perform an O of n time computation across each even number. Okay. If s has only one odd number, one odd number and one even number, so the best case scenario happens when the numbers in S are odd because the algorithm performs an O of log n time computation for each log. If there's only one odd number and the rest are even, you perform a log n computation for that one odd number. Total time for best case, since there's one odd number and the rest are even, n minus 1 even numbers, the time complexity for the even numbers is O of n for each even number, and you only compute O of n for the even numbers, and for the odd one you do O of log n. Thus, the best running case would be O of n. Okay. But if the S had one odd and two even, it would have a best case of what? One odd performs O log n time, two even performs O n time computation. The best case. But you compute an additional O n operation on all evens. So wouldn't it be log n plus n squared? I see where the confusion lies. Let's clarify. You have a sequence S with one odd number and two even numbers. Algorithm C executes O of n time computation for each even number. If you're asking about the best running times in this case, best case scenario for odd number for each even number, total time, even numbers compute 2 times log n. Two times O of n. Constant factors are ignored, so the total time would be, why not? In the case where each even number takes O of n time, you're not multiplying the complexity for each even number. The computation for each even number is done separately and adds up to O of n. So what is the worst case? So how can it say that we have, for even numbers, we have a total running time of O of n squared and then not, and take it away when, in the other example? It doesn't make any sense. How can you now say that even numbers have a total running time of O n squared when before You said it was 2n. You're right to point out the inconsistency in my previous explanations. Let's go over and make sure we got this right. Um, if the sequence S has mostly odd numbers, the time for each odd will be O of log n. If there are two even numbers and one odd, as your example, you would do O of log n, and each even number would contribute O of n times. If there's two even numbers, in the best case, it would become O of n. Worst case scenario happens when all elements are even. In this case, for each of the n even elements, we perform O of n time operations. So but in both examples, you have more than one even number. So it should still be O of n squared. No? I see where the confusion is coming from, and I appreciate your patience. The best case time are mostly odd numbers. Let's go over through the best case time mentioned earlier. One odd number, the computation is O log n. For two even numbers, it would be 2 times. Yeah, we've been through that. It's just telling me the same crap over and over again. For each even number, the algorithm performs an O of n time computation. If the sequence has n even numbers, the total running time is n times O of n, or O of n squared. This is the worst case running time. It's a quadratic because we're performing an O of n time computation for each of the n elements in the sequence. To summarize, best case running time, if they're mostly odd numbers, one odd number, two even, their running time is O of n because the even numbers only contribute O of n separately. Although there are multiple even numbers, like an example of one odd and two even, each even number only contributes one O of n operation. Therefore, adding up to the total computations of two even numbers results in O of n, not O of n squared. Only the worst case, when all n numbers are even, do we get O of n squared. Wouldn't the best case be O of log n and the worst case be O of n? So that's what we're trying to figure out here. It doesn't make sense that you, by adding in a single odd to a CS of n evens, would change the time complexity from O of n squared to O of n. Let's go over it again. You are describing only one odd and one even. Apologies. Let's go. Sorry, I take that back. Technically, it's best case O of n, worst case O n log n. No, the worst case would not be O of n log n. The worst case is n squared, right? Because if you have two even numbers, you have to you have to go like this. You have to say for value in n, if value modulo 2, right? You're going to whatever. You're going to say you perform at this point here, you say perform O of n operation on value. right? So A, you do a linear time thing here, and then you do another one here. So you would do O of n squared. Thanks for the clarification. I understand the approach. Now I understand the approach you're suggesting. I'll walk you through carefully. Let's break down the steps you're proposing. If s equals 2 and s equals 4, an example sequence of numbers the algorithm will execute. For each number in S to perform O and n time, the loop runs O of n times for each iteration. We perform an O of n time operation. The total time complexity is O of n squared. This is because when S equals 2. Worst case time complexity will be O of n squared for any sequence where at least some even numbers, because if there are O log n time computations for odd numbers, the n time operations for even numbers will dominate the total time complexity. If the sequence only contains odd numbers, then time complexity will be dominated by O log n computation for each odd number. It would still be O of n log n at worst. Does not significantly change the overall worst case time complexity, even as even numbers with their O of n time complexity dominate this time complexity. So then the best case. Oh, this problem sucks. Um, Let me see here. Give me 1 second, guys. We're on what, 31? You are doing O of n and O of log n, which is overall O of n. If all entries are odd, your best case is O log n. Worst case is O of n if they're all odd. I don't agree with this. So right, if we have okay, so let me take this, copy it here, and be like, paste it here. What would be the time for a s equals 1, 3, 5? For each of the three odd numbers, the time complexity is O log 3. Since there are three numbers in the sequence, the time complexity would O log 3, 3 times O log 3, n log n. So the best case is if the sequence only has one odd number, meaning that it would perform in O of n log n time. If the sequence had only one even number, it would perform in O of n time. Worst case is O of log of O of n if they are all odd. If they're all even. Worst case, though, no, is if you have multiple even values, like 4, 6, 8, which would be O of n squared. Right? S has multiple even values would be the worst case. I think this is the answer in my opinion. Right? If you have one value in your sequence, if s is equal to 1 is in this case is 1, then your best case would be log n. But if sequence is 2, 4, 6, 8, you would get 2 squared, n squared. Best case scenario. The best case scenario, the sequence S only one odd number. Odd numbers only require n log n time operations, so there's only requires log n. In the worst case, the sequence S contains only even numbers. Even numbers require O of n time computations for each element, n squared. So what would be the overall time complexity for S? Determine the overall time complexity for operating algorithm C. K equals 0. What is it? It's doing a bunch of stuff here. Sequence of integers. So this does say that though, given a sequence of integers, so it's more than one. Odd numbers should be O of n log n. This is assuming S has more than one integer. This is going to be the best case. Get rid of this. This is going to be the worst case. Okay. So we're assuming that S has more than one integer per its definition, right? A plural integers is here. Okay. Cool. Um, Given n element sequence S, algorithm D calls algorithm E on each element S at index I. Algorithm E runs in O of I time when it's called on the element Si. What is the worst case running time of algorithm D? So it runs in constant time, or it runs in time. Yeah, it runs in constant time. Algorithm E runs in constant time when called on the value, specific index value of the sequence. So given an n element sequence, if you call algorithm DE, which runs in constant time on it, algorithm D would run in linear time for every value in D in S. For I in the range length of S, run algorithm E on index. All right, guys, it's almost 10 o'clock here. I've been streaming for almost 3 hours this evening. I know that we kind of slowed down here towards the end as I got into more of these um, abstract problems, kind of thinking more along the like in the eyes of an algorithm rather than just um, given an algorithm. You have to try to put it together yourself. So we will finish up 31, 32, 33, and 34 next time. And then we will jump right into chapter 4 and begin chapter 4, learning all new material and grinding away at some new stuff. So please follow along. The channel is almost to 400 subscribers, so we're moving right up there, and I really appreciate all the support we've been getting. This weekend, where I plan on doing a lot of work on the Small Business Manager and also on Chapter 4 of Data Structures and Algorithms. So big stuff coming this weekend. Tomorrow is going to be Thursday, so I'll be back tomorrow at 7 p.m. PST after work. And so please join me tomorrow. Again, I'm sorry that I kind of was working through these a little bit more, methodical and in my head. But we will get into, putting the small business manager, getting some more features added to this guy, probably tomorrow. Um, yeah, we added a lot of stuff into it. We worked on it for like a good hour and a half, 2 hours yesterday. So I wanted to get I wanted to get a good chunk of this done so we can get on to chapter 4 as soon as possible. So thanks so much for watching, you guys. I appreciate you coming in, and I'll see you guys tomorrow. I appreciate you. I love seeing you guys. So